Welcome to Patterns Physics. I'm Bradford Hill, and this video gives you an overview of the Patterns Physics curriculum based on the Patterns approach. Also, this will function as a short overview of the website. So let's go there. And here's just the homepage. And if you appreciate the depth and detail of a peer-reviewed journal article, here is an article I wrote about the patterns approach in NSTA's journal, The Science Teacher. You can click right there. I already have it open. In addition to this article, though, you have this video. So I want to show you several of the other resources here on the website. I'm just going to go ahead. Zero files under home. You can find a lot of key information there. But let's move right on to, lots of times people want on a single page the overview of the whole course. So here we have it, Patterns Physics. Here's a great image that gets to the heart of one aspect that spirals in the course. So really having students experience and live mathematically modeling the common functions we see. And then you can see throughout the rest of the units in the course, they spiral back to these same four patterns: horizontal line, proportional, quadratic, inversely proportional, and inverse square. We do wait on the inverse square anchoring experiment till later in the year. All right, and then, where do the NGSS performance expectations fit in? So if you just scroll down, you can see, and about how long does each unit take. Unit 1, I'm going to wait till give a brief overview of each unit as we dive a little deeper, but you can just see Unit 1 is about 4 weeks. Here's all the formative and summative assessment opportunities that you have. Unit 2, texting and driving, and onward. I'll let you actually take a look at this and keep this video shorter. So there is all of the performance expectations over the year. Now, with a three-dimensional NGSS curriculum, the proof is in the details. So let's look at the unit level. So I went and clicked on Unit 1. Here we are. Here is a overview video, 40-minute video that if you are completely new to the patterns approach, strongly encourage you to check that out. If you're returning and want to catch some of the updates that we have had over the years with so many teachers contributing and giving feedback, there is a lot of improvements. So here is a shorter video, 15 minutes. Later units, the videos will get much shorter, but being Unit 1 and so many people new to the approach, we thought that level of detail was appropriate. Okay, so here again, you can see the just a snapshot for the unit of the performance expectations. Unit 1 is really that skill building and time on task for one of the biggest ideas in physics. What's even bigger than Newton's second law or conservation of energy? The idea that we can study something in the world, so often we call that a system, collect data, explore patterns, and in physics, that's so often a mathematical model, to better understand that system and predict / influence its future behavior. All right, and then also scientific practices, just so much there. Even without a performance expectation, this unit and time on task with these ideas, critical to student success. All right, then if we scroll a little bit further, here's just another helpful image, kind of zooming in. What is the progression arrow? What's the essential question? And no surprise, how do we find and use patterns in nature to predict the future, make data-informed decisions in the present, and understand the past? And these are those 4 anchoring experiments with horizontal line, proportional, put those 2 together for linear, quadratic, and inversely proportional. And we say inversely proportional to better connect to our math teachers. All right, so hopping forward to Unit 2, which I already have open here. Unit 2, oh, that is Unit 1 because I opened it. Unit 2. This one really does a heavy lift on introducing students to engineering and computational thinking, specifically with spreadsheets. So another big heavy lift unit, and motion, which is not its own performance expectation, but underlies so much of the understanding required in other performance expectations. And then this one really is focused on how do we use STEM to enhance a social discussion around texting and driving. So a neat unit, system analysis is introduced for the first time here. And that's that idea that we really think about what is in the system and how do we break it down into smaller, more manageable parts and productively move forward. All right, to keep this video short, I'm going to move to Unit 3. And you can see we're starting to add in more performance expectations as the year goes on. And let me get down to the arrow. This one is themed around making a bungee jump app for a local amusement park. And of course, that's going to weave in the need to track energy. Again, we're spiraling system analysis. This is that beautiful thing that we always want students to do whenever they have a problem. You know, draw that picture, queue up the information, queue up what you don't know, which will guide your further investigations. Here we use a driving question board to have students start mapping out the unit so they expect what's coming next. And then, of course, we need to get a mathematical model for gravitational potential energy and kinetic energy. And then for this storyline, we also need elastic energy. And then putting it all together with computational thinking to allow students to troubleshoot and rapidly prototype and think through different scenarios and see what is happening in a bungee jump. And then we even throw in some career-connected learning. App Expo Day, you can invite parents, administrators in, and it's a fun day. There's a jump, and it gets years later, students, even as seniors, say that's one of the most memorable things they had in high school. All right, moving on, Unit 4. So again, we got Unit 4 up here, videos, and any video that isn't linked here will be shortly. And then again, this is that impulse, forces, momentum, and here really trying to mix it up, trying to grab students that might not have been as grabbed by the previous engineering projects. Here we're engineering a shoe. So how does design and STEM work together to bring imagination into reality? So design a shoe. So we explore our challenge with human-centered design, you know, our mathematically model impulse cushioning, which is really intuitive. The words impulse is not very intuitive to students, but the idea that you cushion something and that changes the force and time aspect, that is really intuitive, we have found. So that one might surprise some people to lead with that, but it turns out to have worked really well. Then we have a loop or task on momentum, one day themed around several high-speed videos, then Newton's second law, so important in there, and then putting it all together. There is so much informational text going on in this unit too. This is the big lift for informational text. They have to put together words, 2 tables, and a graph all together to make their data-informed decision for their final shoe design. Then moving to Unit 5, again, you can just see these performance expectations growing and growing. And then, how are you hearing me? Super fun hook. You know, you have a student call into another student in your class, and they're in the hallway and they shout, "How are you hearing me?" And that's our driving question. How do we hear someone through a cell phone? So ultimately, they do almost all of the good stuff of a real cell phone communication. They encode information into waves, decode it, amplitude modulation, frequency modulation, all sorts of good stuff. Now, how do we, again, starting off, what's one of the most important mathematical models or, you know, physics equations or concepts there, experimenting with waves. Then to start to introduce this idea that information is in waves, students code their own ultrasound very simply, but they produce a sonogram, a sound image by coding that, and that's live. So they can go and get new data and produce an ultrasound image, sonogram, for a couple different knee injuries. All right, then with that, we have Do cell phones cause cancer? That is that performance expectation around evaluate published materials. That actually had, that's where they need to be masters of that. So we are going through exposure, practice, mastery. So you'll see in previous units building up to that skill of evaluating published materials. Then there is a task around the ear, and that brings up resonance, which is in the evidence statements. And then again, computational thinking, spiraling back, doing much more sophisticated, and they're using the computer to help them figure out the amplitude frequency modulation to encode the information into a wave. And then there's the actual engineering project of pulling that off. It's a great one. This also is one that students have said was one of their favorites of the whole year. Then we have Unit 6, and just look at all these performance expectations from physical science, earth science, engineering, and technology. So this is really our culminating unit. And I'll explain why 7 being 7 is not. All right, when we get to it. So this one is how does STEM inform our future? This is themed on students making a 50-year energy plan. So it starts off with them being introduced to that. And then there is an activity called Voices of the World, where they hear excerpts from interviews from people all around the world affected by power production and climate change. So that's the motivation. And then there's a lot of physics in there, and no surprise that as they need to present their final portfolio, they need to explain the basic physics of how generators work. And of course, we also want motors in there. And one of the most fun motors to play with is a speaker. So they actually make speakers. And again, we just came off of that waves unit. So that's a great connection there. And then they turn it into a generator, an electric guitar. So super great. Electric guitar is a generator taking motion into electricity. Now, because electric guitars are probably not going to power the world, we got to talk engineering and how do you scale up? How do you make and harness enough energy through a generator to create enough electricity? And of course, one of the fastest growing means of power production is wind, and another one is solar. That's why those two are themed that way. And then, of course, there is that performance expectation around wave particle duality and light, and just the importance of solar power. This is actually an engineering slice. So it's not just a 1 or 2 day activity. And also introduces a new pattern beyond the 4 that we've discussed. And then with all of this, they did some background research on the economic impact and the land impact of various power production means, but we haven't figured out the climate impact. And so that justifies in the storyline our deep dive into all the earth science and climate science standards in the NGSS, and it fits beautifully in, really relevant. And then at the end, you put it all together to make your 50-year energy plan with criteria and constraints. You got to think long-term as you increase wind and solar, your reliability is dropping. So you need to, at the same time, look at energy storage and smart grid technology. So it has a lot of complexity, but keeps it fairly simple. So that's worth taking a deeper dive. Many teachers say that is their favorite unit because of the impact, the importance, and just the storyline and the student engagement with it. All right, then to finish this up, let's take a look at Unit 7. And there's no arrow because this is really meant to be 3 separate tasks, and they're about 2 days each. And they get all of the performance expectations around space and the universe. And this is the idea is if you have 2 days before winter break or 2 days before the semester that you might lose because you don't want to start the next unit, here you can put these tasks in and have productive, use every minute. So we got Halley's Comet around the universal gravity, looking at orbits for the performance expectation on motion of orbiting objects in the solar system. And these are interconnected. So they do build on each other, but they are more, drop in, really want to get them used. And yeah, in any case, then we also have understanding the Big Bang. And starting in unit 4, 5, 6, 7, we always have stations. And this is just a great day. It is so fun. These stations are high interest, and you got the James Webb Telescope. You have, how big is the universe? How are we seeing this stuff? So just a great day. So with that, I'm going to go back to our landing page and say, if you want a deeper dive, you see those other videos. And please stay in touch.